What if you take an object, for example a rock, and you cut it in half? And that half you cut it in half again, and again, and again, and again. Then the question arises, can you do that indefinitely? Or will you end up with something that can't be cut in half anymore? Well, the people in ancient Greece, they called it the atom. The atom from the Greek word tonos, which means cutting, and a, which means not. They philosophized that you end up eventually with something that can't be cut in half anymore, the atom. Well, if we fast forward to the modern age, we discover that a lot of stuff in reality consists out of molecules, and the molecules are like this combination of little balls, and we call these little balls the atoms. So we use that Greek word, the atoms, because we thought that's the fundamental building brick of reality, the atom. But we discovered that even inside the atom we can distinguish other particles. So for example, the outer shell is like a cloud of electrons, and in the middle is like the nucleus of the atom, and that consists out of numbers of protons and neutrons. So now we have three other little balls, little particles: proton, neutrons in the nucleus, and the electrons. But then we digged a little bit deeper and we found that the neutrons and the protons, they consisted out of other little balls, and we call them quarks. And quarks and electrons, they are like particles on the fundamental level. They are part of the Standard Model, and we did a lot of research to them, how they behave, and we can describe their behavior by mathematics. And we found that they're not really particles, they're more like waves. They're like excitations of a field. So we call this the quantum field theory. And a quantum field is like a field. It has a little bit of a two-dimensional feel to it, but it's more dimensional, and it spreads out over the entire universe. It's a field. And some would say there are multiple fields, but let's say there's one field, a combined field. And this field has excitations, and they are like spontaneous, and they occur randomly. And excitations that can prolong themselves over a longer period of time, we can perceive them. So for example, we searched a long time for the Higgs particle, and then we couldn't directly find it because it has a really short lifetime. It decays into 2 muons. But we did discover these 2 muons, and this was like a proof that the Higgs particle exists. But if you talk about it like that, like particles that appear and then transform into other particles and then disappear, it all sounds a little bit like magic, right? It's like you pull a rabbit out of a hat and then it disappears and it transforms into a dove, or it sounds like magic. That is because we think about it in terms of particles. But if you think about it as excitations in a field, it becomes more natural, because the field is already there and it spans the entire universe. And these random excitations, they trigger other excitations. So the Higgs particle is like an excitation, and then it goes over into 2 muon excitations in the field. So that's how we can understand reality, not as like a bunch of building bricks in an empty box, but in a field that vibrates and excites.